Network. This is Dr. Prashanjit Dey. Today I'm going to talk about the fundamental of convolution neural network. And at the end of this talk, I will show you by demonstration that how it can be implemented in a real life on different various kind of applications. So I may start with some image recognition, later any other kind of recognitions, and as we proceed, we may also see how it can be used for medical diagnosis in implementation that can be implemented by Python code, by TensorFlow, Keras, or PyTorch. Let us start our journey with convolution neural networks. In the meantime, if anyone having any difficulty to the slide or to my audio, they can interrupt me. They can just unmute yourself and they can ask their questions. I have no problem with it. So as we all know, we know about the images. The images can be black and white image or the image can be the color image. Now, if I look into the black and white image, the image is majorly consisting of lot of pixels. Now pixels are organized in a horizontal and vertical fashion. So we can talk about this as resolution. So resolution is the height of an image into width of the image, and that is the total number of pixels. So if I say my image is 640 cross 480, then 640 is the number of number of column is there in the image. Let me use my pencil. So if the image is 640 cross 480, that means there is a 640 rows are there, columns are there. So this is the width, which is 640, and the height is 450. So that is the normal convention used when we represent the resolution of an image. And number of pixel is the multiplication of them. Now, each pixel may have a single value. If I'm talking about black and white image, in that case, the pixel may have a value like 1 may represent a black pixel and 0 may represent it is white pixel, vice versa. But if I want to talk about the grayscale image, which are majorly used in our domain, grayscale image. So grayscale image is what? Grayscale image means each image will not have the binary value like 0 or 1. Rather, it will have a value within the range of 0 to 255. Image can have any value between 0 to 255. Here you may present 0 as it is a completely black pixel. If I say that it is having a 255, that is a completely white pixel. And in between there will be lots of shades of gray available. So this is the concept of gray image. We rarely use a black and white image. Rather, we use the gray image where each image has value within the range of to 255. Now, here again, the people may ask the question that why go to 255? So, in general, as we can see, that these are the lot of the pixels there in my image, and how much computer memory is required to store that image. So, suppose each pixel, I'm saying that I want to dedicate 1 kilobyte of memory. Suppose I decided 1 kilobyte of memory to store a single pixel in an image. So I want to, I want to have 1 kilobyte of memory to store one pixel. So this will be the number of kilobyte memory I require to store a single image. That is storage requirement. Now 1 kilobyte means what? 1 kilobyte means for, sorry, it is not 1 kilobyte. I would like to say that it is 1 byte. So if I use 1 byte of memory to store a cell, then this will be the number of byte I require to store the image. If I divided it by 1000, then that will be the amount of kilobyte memory I require to store the data. Now, if I consider I need to have 1 byte to store the image, if I that I need 1 byte to store the pixel of an image, then 1 byte is 8 bit, and 8 bit means what? 8 bit means it is 2 to the power 3, or 3 bits. So from there we can to know that if I have 1 byte or 8 bit of memory to represent a particular pixel value, then how many possible values we may have? The possible values we may have from 0 to 2 to the power 8 minus 1. This will be the range of possible values a particular pixel may have, because having 8 bit to represent the value of the pixel, and each pixel may have value from 0 to 2 to the power 8 minus 1, because 8 is the number of bit. So if you simplify it, you will get to know that number of pixel required is basically 0 to 255. These are the possible representation a pixel may have. So the pixel may have a value minimum 0 and a maximum value to the power 8 minus, which is 255. So that is the convention. Now, if you want to say that I want to store each pixel with the help of 2 byte of memory, then obviously it will be 2 to the power 16 minus 1. In that case, the range maybe becomes 0 to 2 to the power 16 minus 1. These many possible scale values we may have in particular scenario. But for simplicity, we always consider that a pixel is stored 1 byte of memory and it will have only 8 bit position values, which can represent 0 to 250 values. The convention. And that is the number of maybe storage and required to store a particular image. Now, why we need less amount of storage space for pixel? Okay. So let me explain. Give me 1 minute. So suppose I am dealing with video rate, where a video, suppose I consider a 3 second video. Suppose let me consider a 3 second video. Now this 3 second of video, in each second, suppose a video contains 60 frames. Suppose there are 60 number of frames or images present in a video per second. Frame per second is suppose 60. So a video having 60 images or frames per second. And if I consider a video of 3 seconds, then it will have 3 into number of images per second is 60, and if the video is VGA, where the resolution is, as I discussed earlier, 640 cross 480. So this is the amount of computational memory required to store the image. Obviously, it is the number of byte. This is the number of byte required. If you divided it by 10 to the power 3, then it is the amount of kilobyte you require to store the data. And that is why we basically use a least number of memory storage to store a particular pixel of an image. That is the limitation while dealing with image data. Now, till now, I was talking about only the grayscale images. Now, the scenario changes when we deal with the color images. Because color image, in case of color image, you cannot have a single value per pixel. Rather, you need to have a different values for a pixel. As you can see in this picture, a particular pixel contain three values. One with respect to red, another with respect to green, another with respect to blue. Here R refers to red, and G refers to green, and B refers to blue. And these are the components, when they mixed it up, they represent this particular pixel. So from there, we get to know, I think everyone is well aware about the RGB model. So RGB is a three fundamental color, and they can represent every other type of color by mixing them. So if I have some red component and blue component and green component in an image, then in combination, they can represent any different color of image. This is a very famous image of Lena, which is used for image processing and computer vision purposes. And from there, we can get to know that all different type of colors can be represented with the help of these three channels, R, G, and B. So if we want to talk about the color video, then things getting lot more complex with respect to memory storage. Because okay, yeah, in the meantime, I would like to request Deepsika. So, if any participant is trying to join, please allow them, because it will be easier for me for the discussion. Am I audible, Deepsika? Okay, so pardon me if there is any communication audio issue is there, but please feel free and interact with me if there is any issue with the audio or the slideshow. So, in case of video, what I was talking about, that video is a already three pixel values is there, and if I talk about 3 second video, then it will be again multiplied with three, and after that, if I multiply it with the number of frame per second, which is 60, and again, if I talk about the resolution of the image, that means the width and height of the image, so there is a lot of memory storage is required to store a color video, and that is the limitation when dealing with the color images. Now, motivation is there. Earlier era, when the Rosenblatt was working, so he earlier people used to have the neural network structure. Neural network structure, the most primitive neural network structure was single layer perceptron. So single layer perceptron was quite easy. There was one input layer and there was one hidden layer. I think those who are familiar with neural network they can understand. So I have some input layer and I have some output layer. So input layer we feed the raw input features, like suppose the input feature is x1, x2, and x3. If the input feature is x1, x2, x3, in that case it will feed these values will be fed into the input layer of the image. After that it will go to the output layer of the image, and correspondingly it perform the task of classification or regression. Like suppose these three pixels is representing an animal, suppose the cat. Suppose these are the three features which we are using to distinguish an animal between dog and cat. So obviously these three input feature will be feed into the input layer, and after that uh, by further processing we will decide whether it is cat or it is a dog. So it is a simple task. That is the job of image classification. Now, what the problem face in single layer perceptron, that it cannot deal with the nonlinear data. And reality, the data or characteristic can be nonlinear. So for that, we come up with the concept of multi-layer perceptron. So there is a input layer, there is a in between there may be lot of hidden layers, and there will be an output layer. So this is the input layer. Hidden layer can be one or more, and there is a output layer. So that is the concept of multi-layer perceptron. Why multi-layer? Because multiple layer is there, and multiple layers means apart from input and output layer, there can be one or more hidden layer is there, and there can be a fully connectivity. Means all the node of the input layer is connected with all the node of the hidden layer, and correspondingly the hidden layer, the first hidden layer, all the node will be connected with the all the node of the second hidden layer. Similarly, the last hidden layer, all the node will be connected with the all the node of output layer. That is the basic concept of multi-layer perceptron. Now, in this age, in this image, as we can see, suppose this is my image. So this is the image which we are representing by an matrix. So you can consider this is the pixel having value 1. This is the next pixel having value 2. This is the third pixel having the value 3, like that. So instead of showing the color of the images, we are showing the pixel values of the image. And in this particular example, I am considering for the simplicity grayscale image. So I am considering a grayscale image where these are the pixel grayscale values corresponding to their pixel position. Now, if we want to use the conventional multi-layer perceptron for image recognition, in that case, you cannot feed a, this is a 2D grid. You cannot feed a 2D grid in a multi-layer perceptron, because multi-layer perceptron, as you can see, you can only feed a column vector. So input layer, hidden layer, output layer, all are the one-dimensional vectors. They cannot take input as a 2D grid. So due to that reason, you may need to flatten it. Flatten it means you will take the first row 1, 2, 3, then 4, 5, 6, then 7, 8, 9. So you are flattening it. After flattening it, all these pixel values or feature values will be feed into the different input nodes of the input layer. So that is your input layer of the multi-layer perceptron. There may be one or more hidden layer, and finally there will be output layer. So output layer may be identification of dog or cat. So in that case of binary classification, there will be two class. One is cat. So if the animal is cat, the image of a cat is there, then it will have a value 1 and it will have a value 0. Similarly, if the animal is a dog, then obviously it will have a value 1 and the corresponding output of cat will have a value 0. So this is how things are tackled in case of multi-layer perceptron. When there was no advanced deep learning model was there, this is how people used to solve image data and process image data by neural network. But there lies one problem, a big problem. The problem is what? Like here in this 2D grid, we get to know that 5 is a pixel which is at the center position. And if I consider the four neighborhood, then 2, 4, 8, and 6, they are the neighbor of the pixel 5. However, as I am considering only the four neighborhood, so 1, 3, 7, and 9, they are not the neighborhood neurons. But when we are flattening this, we are losing out this neighborhood information, because in case of multi-layer perceptron, these 1, 2, 3, 4, 5, 6, 7, 8, all inputs are treated independently. They are not retaining the neighborhood information. So that is a big loss. In case of our visual cortex of human brain, if we want to consider how we see things, so when light reflect in our eyes, we basically store those pixel values in our retina, and after that we send our visual sensor to brain, and brain try to develop an image out of it. So obviously, suppose I'm talking about my face. Now, if my lips are above my ears, or if my ears is above my below my chin, so obviously it will not look like a human image. So what is the problem here? How human brain works? Human brain carefully take care of the neighborhood relationships. Like the lip supposed to be below the nose, and the upper lip should be aligned with the lower lips. The eyes should be in a both side of nose above, and there should be somehow symmetricity of eyes and nose, ears with respect to the mid region of the face. That is a very ideal case of human face. The human face may vary, but I am talking about the ideal positioning of the human face. So in that case, the neighborhood brain, human brain, precisely take care of the neighborhood region of the all input features or the face features. However, our MLP may not treat those features in a similar fashion. So that is why we would also like to take the image as a 2D form and not just a 1D vector form. If we have to use MLP, we have to consider it is a 1D vector, and there lies the problem. We want to treat image as it is. If it is a 2D image, I need to consider it as a 2D image only. And like that fashion only, we want to feed it. That is the motivation of us. Like here in this example, suppose these are the pixels. Now, in these pixels, some pixels have changed their values. As you can see, these pixels have suffered. So this row and this row has suffered from this image to this image. However, if we use the MLP, they may not consider this neighborhood information, like how information is changing. They may be ignorant of it, and there lies the problem with standard MLP. And another big problem, that ideal, the previous one which I have talked about, that is the conceptual problem. Now I'm talking about the computational limitation of it. So suppose for simplicity, I am considering an image with 6 by 6 pixel. So number of pixel is 36. Now, if I talk about the image of 640 480, the number of pixel is this much, 3,07,200. Now, suppose I want to classify whether it is a dog or cat. So number of class is 2. So in a neural network, suppose the number of hidden layer is 100. So basically in the input layer, number of node is 3,07,200. In the hidden layer, number of node is 100. And in the output layer, 2 class, so number of node is 2. So in that case, if there is a full connectivity, so obviously this amount will be multiplied with 100. So that will be the number of weights between input and hidden layer. So this will be the number of weight vectors, means connecting link between the all input node with all hidden node. This will be the number of weights. And in case of hidden and output layer, so hidden node number of node is 100. In the output layer, the number of node is 2. So what will be the total number of link or weights between them? It will be 100 into 2. For simplicity, I have not considered the bias value. So this will be the number of weights you need to train the classifier model. And as we know that in neural network, only trainable parameter is the weight of the neural network, because input is already known, fixed, and the output is again fixed. And number of hidden nodes, these are hyperparameter which we need to fine tune and clean. So in that case, this many number of weight you need to learn or train. Like all these weight vectors will have some value, and we need to get the optimal value of all these W's or weights so that this model works best. And there lies the problem. Training these many weight values with their optimal values. So all these weight values should be close to their ideal value so that the network gives zero error. That is a very difficult job. Because we always need the number of parameter which we need to train or which we need to learn, that should be as low as possible. Suppose I am talking about for simplicity. Suppose you have an equation ax plus b which equal to c. Now if you know the value of x, so how many suppose you need to get the value of a, b and c. How many equation do you need? You need to have at least three equation. So to get the three unknown values a, b and c. So suppose with respect to x1, another equation maybe with respect to x2, another equation with respect to x3, and by solving those three equations, you will get to know the value of this unknown parameter a, b, and c. So obviously, if this many unknown parameter is there, you can understand how many equations you need to solve to get this value. So that is why we always prefer the number of unknown weight values as low as possible, which technically say the number of free parameters. That is huge in case of multilayer perceptron. So that is why we cannot proceed in conventional neural network. We cannot proceed further as the image dimensionality and the quality of the video are keep on increasing in modern era. Due to that reason, we come up with deep neural network technologies. So deep neural network technology says that we do not need to consider image as a one-dimensional entity, rather consider image as it is. So if the image is a 2D grid, we are supposed to consider image as 2D grid only. So we need to store the neighborhood relationship in the image, and we need to consider less number of parameters. So these are the two vital parameters. So now we are moving from conventional neural network to the deep neural network, precisely convolution neural network, where we are considering the input layer as a 2D grid instead of one-dimensional vector, which was earlier used by the feed-forward neural networks, for example, multilayer perceptron. And while taking the 2D grid, we are preserving the neighborhood relation of the pixels. So a pixels and its neighborhood we are considering in case of CNN, which we were not considering in case of multilayer perceptron. Second is the translation invariant. Whenever we take some images, it may happen that our hand may be shaken, So somehow some pixels may be blurred, some pixel may be occluded. So obviously some pixels may be moved here and there. Suppose a human face is there. If I rotate that human face 90 degree, or suppose there is a classifier there whose job is to identify dog or cat. Now, if I rotate the image of a cat, if I move the image of a cat in the overall image, if I zoom out or zoom in the image of the cat, the classifier should not have difficulty to distinguish it from the dog. That is the concept of transformation invariant, or translation invariant is a one type of transformation invariant. Like if I move the object, I should not have difficulty to classify it. Suppose there is a cat picture in this position of the image, or if the cat position in this portion of the image, or if the cat position in this portion of the image, I should be able to identify it. My performance should not depend on the position of the cat in the image. That is called the translation invariance. Similarly, it should also be scaling invariant. Like if the cat size increases, still I should be able to identify it. And rotation invariant. If the cat face is moved 90 degree clockwise or anti-clockwise, I still be able to detect it. So these are the properties a good classifier should have. And due to that reason, we come up with a convolution neural network. That is the motivation or core concept behind the use of convolution neural network. Like suppose now I am going to going a little deeper. So as you can see, these are both bird images. Now, if I want to find a bird, I will not directly go try to find the bird. What should be my first objective? I need to first objective all the edges in the image, because edge detection are the primary primitive first step of image classification. First of all, my job is to find out all the vertical, horizontal, diagonal edges present in the image. After getting all the edges in the image, we can club certain edges of the image, and we can come up with the small features. Like suppose there are few edges which in collaboration creating the smallest feature of the BART classifier model, where it is a big. Similarly, I can use the other set of edges whose job is to identify the eyes of a bird. Similarly, a different set of edges are in combination trying to find out the feature, the beak of a bird. And there may be another set of edges which trying to find out the feather of a bird. So in case of image classification, our first layer job is to find out all the edges present in the image. So suppose this is my input layer, we try to find all the edges present in the image. That is edge detection. After that, we basically club those edges and try to get the teeny features present in the image. So teeny feature detection. Like if you add this certain set of edges, whether it is look like an eye or a claw or a beak or a feather. So after that, when you get the eyes, feather, beak, and clause. So if all those features are present, then you can come up with a better feature, like whether it is a bird or not. So this is the core concept behind the classification of images in neural network. So that is the reason we need multiple layers between input layer and output layer. So we feed the bird images. First we detect in earlier layers, we detect the edges. After that we try to detect the teeny features like beak, claws, feather, eyes. And if all the features are present, then we can identify it is a bird. Suppose it is not having claw. Suppose it has the eyes of a bird, it may be having a beak like a bird, but suppose it do not have the feather like a bird, suppose it do not have a claws like a bird, so it contain two features, but the rest of the feature is absent. In that case, it may be some different animal, but not a bird. So it need to have all the feature to make it bird. So that is how a image classifier works. That is the fundamental concept behind any convolution neural net. Now our classifier behavior should not deviate with respect to the position of the bird. Here beak you can see at the top left, here you can see the beak is at the center. So our classifier performance should not be deviate or confused with the position of these features, because it doesn't matter where the features are there in the image, I should be able to identify it. That is the property of translation invariance. Every good classifier should have it. And the another locality principle. Locality principle also I have discussed earlier. Like obviously the eye of a bird should be close to the beak of a bird. The eye of a bird should not be close to the claws of a bird. So I should give priority to the neighborhood region. Suppose I have identified the beak of a bird, then I will look for the eyes of the bird in the neighborhood of the beak of a bird, and I will not assume that the eyes of a bird will be very farther away from the beak of a bird. So obviously, when I am looking something, I will give more preference to the local region instead of the global region. Suppose you are investigating a crime scene. So in that case, suppose you want to look, suppose some person is stabbed in a room and you came to the crime scene to observe as an investigator. So in that case, suppose you are going, you must be looking for any sharp weapon present in that room. In that case, you will not see the overall room. Rather than you may use some lenses and you will minutely each portion of the room and you try to identify whether there is any sharp weapon available or not. So if we want to look for something, we never see the global image. Rather, we look into the each region minutely that feature is present or not. Suppose I want to look for whether there is a beak of the bird present in the image or not. In that case, we will not see the overall image to look for the beak. Rather than at a time, we will look a particular portion of the image and see in this portion beak of the bird is there or not. It is like you are using some lenses and trying to look each portion of the image whether that beak is present or not. So you will at a time you will consider a particular local region to find out the feature and not the whole image to find out the feature. That is the locality principle. At a time, look at a particular portion of the image and try to find out the feature. So these are the main principle of a convolution neural network. Now, convolution neural network, I assume most of us know how the convolution neural network look like, but still I want to give a brief discussion before starting my hands-on presentation. So in the meantime, anyone having any doubt, like what is the philosophy behind the use of convolution? If anyone would like to discuss about the philosophy or having any confusion, why convolution, then they may ask. So I am waiting for maybe 1 minute and see if
Sir, voice is too low.
my voice is too low. Okay, so there must be some network issue. Am I audible now?
Yes, sir.
Okay, okay.
Now,
It is
So,
okay
so
now.
sorry
It's
about
okay.
sorry. You were saying something.
no, sir.
Okay. Is there any confusion related till now? Is there any doubt? Okay. So I am assuming there is no confusion. And please, if there is any audio issues there in between my discussion, you can let me know. You can interrupt me and let me know. I will take care of that. Huh? There should not be any technical glitches. If there is any, kindly let me know as early as possible. So let me proceed with the next few sessions. So convolution neural network. Actually, convolution neural network is a deep neural network where it is having an input layer. There is a lot of hidden layers and there is a output layer. Now, as it is a CNN convolution neural network, our input will not be a 1D vector, rather it will be a 2D grid. So let me change the color of my pen. Let me. So instead of 1D, it will be a 2D grid. It will be 2D grid of image that will be fit into the neural net hidden layers of convolution neural network. Now here in CNN, there is a lot of different type of hidden layer is there. It is not like a multi-layer perceptron or any other feed-forward neural network where majorly all the hidden layers having the same characteristic. Here we have a type of hidden layer which we call the convolution layer. After convolution layer, there may be a pooling layer. And this two layer can be repeated multiple times. That means after that, there can be another convolution layer. There can be another pooling layer. And these two layer in combination can be repeated multiple times. After there, there will be a fully connected layer. There will be another dense layer and the output layer. Output layer is always a 1D because end of the day you need to classify it is in one of the C categories. Now, so output layer is always one dimensional. That is the concept. So convolution layer, this one is the hidden layer, convolution layer. And why it is called convolution layer? Because it contain a convolution filter, which I am going to discuss. The concept of input output channel is also I am going to discuss very soon. Padding is related to convolution layer only. Stride is there. Pooling layer is the next layer. So after convolution layer, there is supposed to be a pooling layer. So let me discuss them one by one. Now, till now, I am not going into the mathematical detail of it, but what I can tell you that convolution layer in convolution neural network, the input image is not a 1D image. Input here is a 2D entity, two-dimensional entity. So if the input is a two-dimensional entity, now as I discussed earlier, the input is 2D. If the hidden layer is 1D, it will not work. If the input is two-dimensional, the hidden layer is must be of two-dimensional. And because this may be the first hidden layer, after that there is another hidden layer 2, and after that there may be another hidden layer 3. So if the first hidden layer is one dimensional, in that case, uh, the second hidden layer will receive the image as 1D entity, which is not acceptable because for the second hidden layer, first hidden layer is basically its input hidden layer. For the second hidden layer, the first hidden layer act as an input layer, and input, if the input image is 2D, you are not supposed to represent the image in 1D. You will lose out the neighborhood information. That is why in convolution neural network, if the input image is 2D, the hidden representation should also be two-dimensional. Now, there is a lot of mathematical detail by which we ensure that it will have the locality principal property and it will have the translation invariance property. That I am currently skipping, but I will mathematically, this is there. I am going to share the slide as well. But fundamentally, I am going to explain this thing to you. So suppose this is my, suppose you want to find the beak of a bird. Now this is called the weight tensor or weight vector. This is called weight vector, and a vector, when a vector is more than two-dimensional, it is called as weight tensor. A tensor is a multidimensional vector. So weight tensor. So if you see in this example, the input is two-dimensional. Its coordinate value I and j. And the hidden layer is also two-dimensional. In this case, it is also ij. So the weight which is connecting these two input will have four dimensions or four coordinates. Like if I go back in the previous example, for the simplicity of understanding, let me go back. So in this example, suppose this is the pixel in the input layer. In our neural network, we can consider this is the node in the input layer, whose coordinate value is k and l, and this is the node in the hidden layer whose coordinate value is I and j. So the weight which is connecting this input neuron with the hidden neuron will have four indices. Ij is the index of the hidden layer and hidden node, and KL is the index of the input node or neuron. So it is having the four indices. Now suppose your job is to find the beak of a bird. Now, as I told you earlier, the beak may be present at any place in the image. It can be at the top left, it can be at the center, it can be at the bottom right. So here, as you can see, this weight vector is dependent on the position of the input node. It is dependent on the position of the hidden node. It should not be dependent on the position of the hidden node, or it should not be dependent on the position of the input node. And that is the concept behind translation invariance. So we have done some mathematical computation, which I am currently skipping because it may be little difficult. But those who are interested, they can communicate with me, and I will explain it to them. So by which we come up with, so if you do some computation, then we will come up with a weight tensor which is independent of the position of the input pixel. So a shift in the x input should simply lead to a shift in the hidden representation. So here, as you can see, here it is not depending on the pixel position like xij. Rather, it is depending on the neighborhood, like how many pixel we are going to consider. So this is the concept of translation invariance. That is the first property of convolutional neural network. So I should be, suppose I want to find the beak of a bird, so I will able to find it whatever be its position. This weight tensor, this is actually the feature detector. This is the feature detector. In case of convolution neural network, the weight vector or weight tensor are the feature detectors. So in my convolution neural network, I will have multiple such feature detectors. So in a convolution neural network, we have a convolution layer, and that convolution layer contain lot of feature detectors. Maybe there may be one feature detector whose job is to find the beak of a bird. Another feature detector try to find the eyes of the bird. The third feature detector tries to identify the feather of the bird, and the fourth feature detector may be trying to identify the claws of the bird. And if all the feature detector able to find all the features of the bird, we can say that the image possesses the bird. So that is the concept. Now this feature detector is invariant of the position of the object rather than it just looking throughout the image. So this weight vector is not changing. So whatever be the weight vector in here, the weight vector will be same if I would like to look into this region of the image. That is translation invariance. Now another property of his neural network is that it is translation invariant. Normal MLP, what happens? Suppose this is my input layer, and in input layer, suppose there is a three node, node 1, node 2, and node 3. And suppose in a hidden layer, two hidden node is there. hidden node 1 and hidden node 2. In that case, all these input node are connected with hidden node 1 and all these nodes are connected with the hidden node 2. So there is a full connectivity is there in multilayer perceptron or any other feed-forward neural network. But here, as you can see clearly, there is no full connection. For computation of these hidden node value, for the computation of these hidden node value, I am considering only these input nodes. I am not considering the non-neighborhood pixels. I am not considering the non-neighborhood pixels. I am ignoring these pixels. So that is the another advantage of convolution neural network from multilayer perceptron. We are ignoring the non-neighborhood pixels while computing the value of the hidden node. Not like multilayer perceptron. In multilayer perceptron, if you can recall, suppose this was the input layer where suppose maybe four nodes are there. Suppose in a hidden layer there is a three node is there and all the input node is connected with the first hidden node. Now while computing this hidden node input value, we were considering what? Sum over of suppose there is a four node. No? So sum over of four, suppose xi is the first feature, first input node. So here I equal to 1 to 4 xi and that will be multiplied with w hidden node 1 and after that the input I value. So this is how we compute the need values. So if we consider I as 1 then it will be x1 into w11 plus for this node it will be x2 dot w12 plus x3 into w13 plus for this last node it is x4, so x4 into w14. This is fixed 1 because we are computing for the first hidden node and this is I, it is keep on changing 1 2 3 4 and this, so as you can see this is the net input to this hidden node. Now in MLP, this hidden node having some activation function. Suppose it is having ReLU activation function, ReLU. So we apply a function ReLU over it, and if the output is positive, then it will have a value, whatever the net value, that will be the output. And if it is negative, in that case, the output is zero. In case of ReLU activation function. So obviously, for the computation of the output of this hidden node, all the input samples take into competition, take part in competition. But here in this case, for the computation of this hidden node, only these input nodes are participate in the competition. So they are taking part in the competition, but rest of the pixels which are not in neighborhood, they are not take part into consideration. So we are not considering all the input nodes or features or neurons for the computation of the hidden node. That is the another advantage of convolution neural network with respect to multilayer perceptron, which we have discussed while we are discussing the locality principle. So we are considering only the neighborhood and we are discarding those pixels which are outside this neighborhood delta. And in that case, this vector V, weight tensor or kernel, this is actually convolution kernel or convolution filter. So many books you may see that convolution kernel, convolution filter, then people say weight tensor, feature detector, they are basically same. They are synonyms with respect to the topic convolution neural network. So here, this convolution kernel now throughout my discussion, I can use this term convolution kernel or convolution filter or feature detector or weight tensor interchangeably. So they are basically conveying the same meaning. So here in this case, if we consider this image is a, pixel grid, then this is a weight vector or weight tensor or feature detector or kernel or filter, they are trying to find the feature. Why I am talking it is a feature detector? It is trying to identify the feature beak of a bird. So what will be its output? Its output will be zero because there is no beak of a bird. Now when it will move further, then it will able to identify the beak of the bird is present in that region. So it will send an output 1. So a particular hidden node in the convolution layer, a hidden node will send a high value 1 when it will able to find the feature, and it will pass a value 0 if it fail to identify or find the features. That is the working principle of a convolution neural network. So as you can see here, the output of corresponding position, it will send a output 0. Here it will send a output 1, that I have find out the feature of the bird or beak of the bird. So this kernel is not going to change. This kernel or weight vector will have same, and it will look throughout the image, and it will search for the beak of the bird. And if it find out the beak of the bird, it will have a 1 output. If it fail to find the beak of a bird, it will have a 0 output. So you can say a beak is a feature, so you can call it a beak detector. So as till now, we have understood that convolution neural network has a lot of filters or kernels, and the job of each kernel is to detect a feature. So, in the initial convolution layer in the convolution neural network, initial layer may contain the kernel or feature detector like horizontal edge detector, vertical edge detectors. So, that will be the kernels in the initial convolution layers. As we go deeper, the more deeper convolution layer may contain more complex feature detector like beak detector, claws detector, feather detector like that. And in the higher layer, we may try to find out the head of a bird, body of a bird, tail of a bird, legs of a bird. So this kind of higher version of the feature we will try to detect as we go deeper. Till now we have discussed what this is my image, and there is a lot of so there may be lot of convolution layer and pooling layer. Now I have talked about, so this first initial set of convolution layer will try to detect the edge features like vertical edge, diagonal edge, horizontal edges. The next sequence of convolution layer try to detect more deeper features like beak of a bird, feather of a bird, and after that, the higher version of the convolution layer will try to detect more higher version features like head of a bird, a tail of a bird, body of a bird, legs of a bird, like that. And finally, when all the feature we have accumulated, we will apply a flattening layer along with a dense layer to overall come up with a picture whether it is containing the bird or not, which will be fed into the final output layer for classification. So this is how it works. This is your input image 2D, and this is your weight tensor or filter or kernel or detector, whatever name you prefer, you can say, and it will hover. It will hover throughout the image, and if find out the feature, it will have a high output 1. If it fail to find the features like metal detector, when it find the metal, it buzz with high noise, and if it fail to find the metal, it do not make any noise. So if it find out the feature, it will have a very high value 1. And if it fails to find the feature in certain region, so feature is not there in this region. So when it will hover through this region, the output will be 0. But if it find out the feature, then it will have a high output in the hidden layer. That, okay, I find out the feature. That is how it works. So, in case of motivation, so suppose I want to identify the feature of Einstein, image of Einstein. So, we are not going to consider all the 1 million pixels. Suppose the image is 1000 cross 1000. So, and in that case, if we consider 1 million hidden units, so these many number of here weights you need to train, which is not logically possible or computationally easier. So rather than we basically use multiple filters and try to identify different features, and all in combination will try to help me to find out whether this is an image of Einstein or not. So we'll club them and we'll try to find out, okay, this is the picture of Einstein. And this is how human face identification done by CNN models. So that is the core difference. And CNN is a particular neural network. It has the capability to use the GPU. As you can see in the previous image, you can see lot of the feature detector are there. There are how many feature detector? Four feature detector are there, and they can work independently. They can work independently. So if you have a privilege of having a GPU kind of system, you can use thread programming or parallel programming. You can use GPU, and GPU, each GPU will be dedicated for identifying a dedicated feature. So you can use a GPU to identify the hairs. You can use another feature detector to identify the eyes. Third feature may be the mustache. The fourth feature may be the maybe the chin area of the person, and all these featured or convolution layers can work in parallel, or convolution kernels precisely. I need to say all these convolution kernel can work in each different GPU system, and they can work in parallel and come up with a answer that this image contain the Einstein or not. So CNN are very good. They can easily used by GPU system. Parallel processing are a lot more easier, which may not be possible with normal feed-forward neural networks. So that was the another advantage. So it can leverage the GPU benefits. Now, fundamentally, there is one question people used to ask, that what the operation we are doing in a convolution layer, that is a convolution operation or a cross correlation operation. So mathematically speaking, in a convolution neural network, whatever operation we do, they are basically cross correlation operation. They are not convolution operation. Mathematically, there lies a simple difference. But as you can see, that the output which you are getting by using the convolution filter in a convolution neural network, though mathematically they are cross correlation operations, but they give us the same output as convolution layer. So due to that nature, we used to say it is a convolution neural network. So why convolutional neural network? Why convolution? So basically, it use a function cross correlation for identifying the feature, and that cross correlation function give us the same output as the convolution function. Due to that nature, we call this feature detector as convolution kernel. That is the meaning behind the nomenclature of convolution neural network. So as you can see in my demonstration, what is cross correlation operation? Suppose this is your image, and this is your weight vector or weight tensor or kernel or filter or feature detector, whatever name. So basically we multiply 1 with 0, then 1 with 1, 2 with 3, and 3 with 3. So this is the output value. So if I apply this kernel over my image, this portion of this image, then I will get a output 19. So this is my image, sorry. This is my kernel, and now I'm going to apply this kernel over image. So suppose this kernel is going to detect some feature. So it is a type of feature detector. Now let me change the ink color. So firstly, I will apply this kernel over this portion of the image. It is going to give a 19 value. After that, I am going to apply this kernel over this portion of the image. It may give me another value, maybe x1. After that, I am going to apply the kernel over this portion of the image. It will provide me a value x2. And after that, I am going to apply this kernel over this portion of the image, which may give me a value x3. So this will be my hidden layer representation. So my input layer is this kind of 2D image, and my hidden layer is this kind of hidden representation. It is also a 2D representation, but the resolution earlier it was 3 cross 3. Now the hidden representation is 2 cross 2. So I have lose out the resolution of the image. There is another issue I'm going to discuss later, but that is how cross correlation operation works. So in our convolution neural network, we mathematically use cross correlation operation. Now you may ask me why then we call it a convolution neural network and not cross correlation neural network. So let me now try to understand the working principle of convolution operator. So in case of convolution operator, what happens? This is your kernel and this is your input layer. And convolution basically works in a different way. So it first multiplied like this. So basically 3 will be multiplied with 1, and after that this 2 will be multiplied with 1, and this 1 will be multiplied with 3, and this 0 will be multiplied with 4. So they are basically work in a opposite anti-clockwise direction. So if you do the computation, then you will get the output 0. Now you can see if I apply convolution, output is 0. If I so if you use the convolution, you will going to get the output 8. If you use cross correlation, you can get the value 19. So you may say, okay, then cross correlation and convolution are not same. Why we are using it? Very good question. So here, basically, if you just flip this image both horizontally and vertically, you can see you will get coming up with the same result. So in this example, if I flip this image both horizontally as well as vertically, then you will see you will come up with the same 19 value. You can try it in your home. So I just, or you can kernel. Suppose you are flipping this kernel. I have what? I have both horizontally and vertically I flipped it. So mirror as well as flip. If you do that, and after that if you use the convolution, so after, if you use this weight tensor and if you use the same convolution function, you can check you are going to get this value 19. So basically convolution, if you flip it and mirror it, it is going to give you the same answer like cross correlation. And that is why though we use cross correlation operation mathematically in a convolution neural network, but still it works as same as convolution neural network. And that is why we call it a convolution neural network. Now, previously we have faced few fundamental problems, which I'm going to discuss one by one. And these questions are very interesting. Let's see. I think rather than talking about this, let me discuss with an example. Suppose this is my input image. This is my kernel. So input image is 3 by 3 and kernel is 2 by 2. Now, if we see, I am applying over this portion of the image. I am going to get a value 19. Now I am going to use on this portion of the image. Let me apply on this portion of the image. I will get some value of 25. Now I am going to apply on this portion of the image. So apply on this portion of the image. I am going to get 37. Okay. Now I need to apply on this portion of the image, this kernel. So I am going to get a value 43. All good. So my input representation was input layer was 3 cross 3. I have applied a weight tensor or kernel 2 cross 2, and my hidden representation is 2 cross 2. Very good. So we are losing the dimensionality. So input image was 3 by 3, kernel I have used 2 by 2, and the output is 2 by 2. So input layer resolution we are losing, and this is the formula. So this is the height of my input image, this is the height of my kernel, and this is plus 1. This will be my size of the output height. Similarly, this is the input width, kernel width plus 1, and it will represent the width of my output. Am I clear? So we are losing the resolution of the output window. So that is one limitation that can be resolved. That can be resolved by the padding technique that I will discuss later. Now, before that, I want to show you how a kernel can help us to identify a feature. For simplicity, let us start with a very basic task of edge detection. Suppose this is my image. Suppose this is my image. For simplicity, let us consider all one means a black pixels and this zero means the white pixels. So you can consider this as this is the okay. Uh, okay. So black color. If we consider black pen, I hope this is black pen. So basically, these portion are black. Sorry about my writing. This portion is again black and middle portion is white. This is my image. This is my image. And in that case, my job is to identify the horizontal edges. That means my job is to identify these horizontal edge. Sorry, extremely sorry. My job is to find out these vertical edge as well as this vertical edge. So these are the vertical edges I need to identify. So I need to identify this edge and I also need to identify these edges. So these two horizontal edges I need to identify. So what kind of classifier, what kind of kernel I need to use to, what kind of kernel I need to use for the detection. For simplicity, let me consider a kernel of +1 -1. So this is my input image. Good. Now I am going to use a kernel with +1 -1. And now I am going to apply this kernel on the total image. So first this kernel will be applied on this part of the image. So what will be the computation? It will be 1 into 1 plus 1 into -1. I think I should use the different color. So let me use a color like more deeper color. So let me use a blue color. So in that case, 1 into 1 or 1 into -1. So output will be 0. So in that case, the corresponding hidden value will be 0. Let me compute this for the second set of image, part of the second region of the image. 1, 0 and 1 -1. What will be the case? 1 into 1 plus 0 into -1. In that case, 1 into 1, 1 and 0 into -1, 0. So it will have a value 1. So earlier the input was output was 0. Now output is 1. Similarly, with this case, you are going to get a output 0, 0, 0. Then you will get a -1, then 0, and this phenomenon will repeat it. If you try it, you will come up with an answer like this. So if this is your input representation, your hidden representation will look like this. Now here you can clearly see that there is an edge, vertical edge, and there is another vertical edge. So by using this kernel, you can easily identify whether there is any vertical edges there in the image or not. So this was my image. This is the kernel I have used, and the hidden representation which I have got here, that clearly state the presence of vertical edges in the image. So for better clarity, I have drawn it earlier. So see, if you apply this kernel over this input image, this is the hidden representation you are going to get. And here you will clearly see there the presence of vertical edges. So I can consider this kernel or filter as edge detector, or more precisely vertical edge detector. Similar question I can ask you in future, like whether there is any horizontal edge present in the image or not. So accordingly, you have to come up with a kernel which will be able to identify the horizontal edges present in the image. I hope it should be not difficult for you. So you can simply use a transpose version of this vector that can be used for the detection of horizontal edges. So this is how kernel actually work, actually help us to detect the features. So similarly, you can see I can use horizontal edges, vertical edges, and I can use both of the kernels. Suppose the K1 is vertical kernel and K2 may be the horizontal kernel. And if I use these two kernels in my convolution layer, in that case, in combination, they will be able to detect all the edges present in the image. So this is the image I fed into my model, and I have used the earlier two kernels like this kernel and the transpose version of the kernel. I have used the two kernels in my convolution layer, and after that I add those kernels and come up with this image. This is the image which basically captured both the horizontal and vertical edges. So this is why the kernel also called as feature detectors. Now, in my example, I have considered as this was a very simple task, I manually configured my kernel, like kernel having a value 1 minus 1 or 1 minus 1 transpose. But in reality, when you are trying to find out the beak of a bird or feather of a bird, obviously you don't know that what specific feature you want to identify. So in reality, the kernel is not some value which we are pre-computed and feed into the model. Rather, it will be a vector which whose value we have to compute by looking into the relationship between the input and the output of the image data. So it is basically a learning concept, not the data will be automatically given to you. So edge detector is very simple. However, as we look for larger kernel considering successive layer of convolutional, it might be impossible to precisely know earlier what the kernel or filter is. Our job is to learn and know based on the data set what should be the value of kernel or what should be the value of weight tensor. That is the only thing we learn in our convolution neural network. Okay, feature map. Feature map is another important concept, and the receptive field are the important concept in a convolution neural network. Suppose this is my input feature in the ith layer. Suppose this is the kernel I am going to apply. So obviously this is the output I am obtain. So this is my input image, this is the kernel, and this is the output we have obtained. So in that case, what is feature map and what is receptive field? So I can say, suppose, so here in this example, these four input pixels contributed in the computation of the hidden node value 19. So in that case, I can consider this 19 is the feature map, and this all this input which helps me to compute the value of 19 are the receptive fields. So this is my receptive field and this is my feature map. So that is their definition. And if I go further, if I go to the next layer, like if I apply the same kernel on this second layer, then we'll get the output like this in the third hidden layer. In that case, for 228, this is my receptive field, this is my feature map, this is my receptive field. So for this is my receptive field in the I plus 1th layer, and this whole image is my receptive field in the ith layer. That is the concept of receptive field and feature map in convolution neural network. Okay. Now let me discuss padding. Why padding? So in previous slide we have discussed, suppose input image if it is 3 by 3 and if the kernel image is 2 by 2, then output image is also 2 by 2. So we are losing the input resolution by 1 because input was 3 by 3. After applying convolution, image become 2 by 2. Or if I go back to the previous slide, then it was 3 by 3. After first convolution layer, it become 2 by 2, and after second convolution layer, it become 1 by 1. So we are losing the resolution of the image, which may not be desirable every time. That is why a concept like padding comes up, which tells that use some padding in the left side, right side, top side, bottom side of the image, and after that apply kernel so that we do not lose the resolution of the image. So let me explain with an example. This was my earlier image. I have used one padding in the left side, one padding in the right side, one padding at the top, one padding at the bottom. You can call it zero padding. Zero padding means availability of padding. Many times people make mistake. What is zero padding? Zero padding means there is a presence of padding and padding value is zero. So that is called zero padding or same padding. In Keras, you may have heard the term same padding and valid padding. Same padding means padding is present while applying convolution neural network, and the zero padding means padding has applied and the padding value is zero. That is why it is zero padding. So in here we have used zero padding, and if we apply the zero padding in the input image, then input image from 3 by 3 it has become 5 by 5, and after applying 2 by 2 kernel, this will be my output image. So input image was 3 by 3. After applying padding, it has become 5 by 5. If you apply 2 by 2 kernel on it, then the output image will be 0 by 0. Advantage of padding is that you are not losing out any boundary information, which you may lose if you do not use the padding. So this is how it will look like. Now here one tricky problem is there. As you can see in this example, actual input image was 3 by 3. After applying padding, the image become 4 by 4. That is also not required from our end. We want to have same resolution of the image, or we want to reduce the resolution of the image. But no, by no means we want to increase the resolution of the image. It is never required in a neural network or a convolution neural network to increase the resolution of the image. Yeah, resolution of the image can be same or it can be decreased, but there is no logical advantage to increase the resolution of the image. That is why here lies the problem. That is why we always suggest in a convolution neural network, always go with the odd sized kernel. So always consider odd size kernel. If you use the even size kernel, this type of problem you may face. If you follow my philosophy and if you use odd size kernel, suppose instead of 2 by 2 kernel, if you use 3 by 3 kernel, you can check, you will always come up with a output will 3 by 3, because input height was 3. Then kernel height is, so if I consider kernel height also 3 instead of 2, and padding is there is above, below, so padding is 2 and plus 1. So 3, 3 cross out and it will come up with a value 3. So height will be 3 and same will goes for the width. So it will be a 3 cross 3 image if we use kernel 3 by 3 instead of 4 by 4. And in general, there is another very tricky concept. Many people are got confused. I suggest that kernel, you cannot apply padding only at the top but not at the bottom. You cannot apply padding only at the left, not at the right. If you apply padding, you have to apply padding at both end. So that is why, in general, when we write padding 2, though mathematically here we are writing padding 2, but basically when we write code, if I write the horizontal padding is 1, that means padding will be applied both at top as well as bottom. If I write the padding width is 1, then there will be padding applied in the left as well as in the right. So overall image resolution will be increased by plus 2 in both end. Okay, excuse me, give me a moment. I have to receive a call. Hello. Okay, I'm in a meeting. Can you tell me what is the query regarding? No, 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 not required, madam. Thank you. Okay, sorry to disturb everyone. Where was I? I was talking about the significance of padding so that you do not lose the resolution of the image. However, I suggested to go for odd size kernel, and I also informed that in coding you have to use horizontal and width padding, and you need to precise the value one. And one by one, you are suggesting that the padding will be applied both from both direction, so mathematically it will look like this. But when you will do coding, you will apply padding value like 1, 2 like this. So if I write horizontal padding as 1, then basically 2 padding will be added, one at the top, one at the bottom in mathematically. So that is the concept of padding. Now there is another concept is there, stride. Stride is what? Suppose your input resolution is too high. Suppose you are working with some 4K images where resolution can be 2140 cross 1800. Suppose this is the resolution of the image. In that case, if you want to have a 3 cross 3 kernel and if you want to go through the whole image, then it will take a lot of time to compute the hidden node value. So I am talking about, suppose this is your input image and suppose the resolution of the input image is 4000 cross 36,000. Sorry, 3600. If we this is the resolution of the input image, and if you are using 3 cross 3 kernel, then it will take a lot of computation to get the hidden node values because the resolution is too high. In that case, to speed up our learning, we use the stride value more than one. Stride value more than one by means you are not going to go horizontally one by one. Rather than you will skip. So you can consider this part of the image. After that, you will consider this part of the image. After that, you will consider this part of the image. So you are skipping intermediate regions in the input image, both in the horizontal direction and the vertical direction. It is used to speed up the learning when the resolution of the input image is too high and it may take too long time to compute the hidden representation values. Let me demonstrate with an animation. This concept is also called as downsampling. Suppose this is my input image, this is my kernel. So now by default stride is 1, but here in this example we are using stride 2. By stride 2 I mean I will apply this kernel over this portion of the image. After that I will apply, so this may be the position 0. I have applied this kernel over this position of the image. After this is my position 2, this is my position 1, this is my position 3. So after 0th position, I will directly apply the kernel next time on this from position 2. Position 2. So I am skipping the in-between region. In-between region means I am talking about this region. So this region I am skipping. In ideal cases, we consider this region first, 0th region first. After that region 1, after that region 2. But if I use stride with 2, in that case, I will skip the middle region. I will skip the middle region. I will consider this part. I will consider this part. I will skip the middle region. That is the, and as I am skipping the middle region, all the computation of the middle region will be ignored. So as you can see, I have considered this region. I got a value 19. After that, I have considered this region. You can see this region has been ignored. And 45. And similarly, this is 0th position, 1 position, 2nd position, 3rd position. So here also, after considering this position, we are going to consider this position. And in vertical direction also, we are going to ignore this middle position. We are going to ignore this middle position value. So you can see I have considered this position and then this position. So this is the advantage of stride. Stride drop the resolution of the image by 2. So earlier it was 4 cross 4. Now it is 2 cross 2. So in a roughly you can say it basically drops the resolution of the image by 2. It halves the image resolution. And due to that reason, this concept is called downsampling. It used to speed up the computation, though it may lose certain information present in the image. As you are drastically reducing the resolution of the input image, you may lose out information in this approach, though it will speed up your learning technique. Okay, so till now I have discussed. I would like to take a 1 minute break. In that time, if any participant having any question, then they can raise and ask me.
Sir, good afternoon, sir. Hello, sir. Good afternoon, sir. Hello. Hello.
Sir is currently having a break. You can have your questions ready, and after sir comes, you can shoot
Okay.
your questions to him.
Thank you. Thank you. Thank you, madam.
Hello, dear participant. Is there any question? Please ask till now, because very soon we are going to start with our implementation and demonstration. So, if anybody having any question, please ask.
Sir, good. Hello, sir. Good
Yes,
afternoon, sir.
please. Good afternoon.
Sir, one doubt, sir. Actually, that is the pooling layer, sir. Actually, how to find out, sir? Pooling layer and the dropout layers.
Okay, very good question. I have still not started the discussion on pooling layer. So I think let me conclude the rest of the part. After that, let me receive the question because I have not started the discussion on pooling layer. Okay, so no issue, sir. I hope I will get your answer throughout my discussion, and I will get back to you.
Okay,
So
sir.
so I have discussed till now the stride, why stride should be greater than 0 and why it should be 1 based on the scenarios. Now I am going to discuss another core concept of the CNN. That is again a very interesting question. So suppose, let me show you this scenario. Suppose your image is a color image, but for the visual limitation of us, I have considered a color image where I have considered only the red and green component, only the red and green component. So if you take an image, this may be the value of the red components, and these are the value of the green components. So in that case, my image will be represented by a 3D data. So where 3 cross 3 is the width and height of the image and 2 is the number of channel. In my case, there are two channels, red and green channel. So this is my input image. Now, if there is a red channel and green channel, two channels are there in my input image, then I must be having two number of kernels as well. One kernel with respect to the red channel and one kernel with respect to the green channel. So this kernel will be applied with the red channel. This kernel will be applied with the green channel. And after that, I will come up with these values. So you can see I have applied 1 into 1, 2 into 2, 3 into 4 and 4 into 5. So this is maybe some value I am going to get 1 plus 2, 3 plus 12, 15 plus 20, 35, something. Sorry, it was 5. So 5, it will be 27 and it will be 20. So it may be having some value kind of this. So here it will be 0 into 0 plus 1 into 1 plus 2 into 3 plus 3 into 4. So it will have a value like this. So this is 0 plus 1 plus 6. So 7. 7 and 14 is 19. So this was 19 and this value may be 7. So if you add them up, because it is 1, 5 and it is 12. So 17 plus 20 is 37 plus 19 it is 56. So this 56 value we are going to get over here. Up to this, is it clear? So if I am having, till now I was talking about only one channel, grayscale image. Now I am talking about multi-scale image, where for simplicity I could have considered three channel, red, green and blue. In that case I needed to consider another matrix, but for simplicity I have kept only two channel, red and green. So this is my red channel input, this is my green channel input. If there is a two channel are there in the input, the number of kernel also should be equal to the number of channels. So here I am used two kernels. Kernel 1 with respect to red channel, kernel 2 with respect to green channel. After that I have applied the kernel 1 to the red channel, kernel 2 to the green channel. And when we get the value, we basically add these two value to come up with a pixel value of 56, which is the its corresponding hidden representation. Similarly, I will apply, let me change my pen color. Similarly, I am going to apply this kernel over this portion of the image in the above pixel. This kernel will be applied over this portion of the below image. So green channel kernel will be applied with green channel input. Red channel kernel will be applied with red channel input. And accordingly, we may get some other value which will be fed into here. Similarly, I will get some value x2 and I will get some value x3. So for this input, I will get this kind of hidden representation. I have done implemented the animation for it. Just see. So this is how you are going to get the value. Now, a triggering question is there. As the input channel was three-dimensional, multi-dimensional, this is the number of input channel, red, green, this is the height width. And if we apply this kernel, you are going to get output which is having only one channel. So we are losing out the output channel. If there is a multiple input channel, the output channel is always one. Now, suppose this is your input image. This is your first convolution layer. This may be a second convolution layer. This may be a third convolution layer. In the first convolution layer, number of input channel was 2 cross 3 cross 3. Next time it is 1 cross 2 cross 2. So in the next layer, this layer is receiving, it's not receiving multi-input channels. It is receiving a single input channel. So it is not retaining all the information present in the input, because input was multi-channel. There was two channel. But after the first layer, the channel is reduced to one. Even if the input was multi-channel, the uh, input channel was multiple, but output channel is one. Here output channel is one. So for the next layer, the input channel has become one. It has lose the information related to the channel. So due to that reason, we have to go further and think in such a manner that if the input channel is multiple, the output channel should also be of multiple value. How we can do that? Let us proceed. So now this is my red channel input. This is the red channel kernel. This is the green channel input. This is the green channel kernel. And this is the output. So even if the input channel is 1, output channel, even if the input channel is 2, output channel is 1. Now we are going to use another set of kernel on this same image. The image is same, and I am going to apply another set of kernel on this image, and from there we will get output with respect to another channel. So earlier channel was 1 output, now I am getting output channel 2. So basically I am considering if the input is 3-dimensional, I have to use a kernel which will be a 4-dimensional tensor. And that is why from the beginning of our talk I was using the term tensor over vector, because here, as you can see in this example, the kernel is a higher dimensional vector. That is why I was using the term tensor. So kernel, as we know, it is nothing else but a set of weights, weight vector or weight tensor. And if the input channel is a multiple input channel is there, and if you want the output channel also multiple, so you have to consider the kernel which will be of higher dimensional. So in case of kernel, the first dimension represent the number of output channel, next dimension represent the number of input channel, and third dimension is represent height, fourth dimension represent the width. And this is how a kernel or weight tensor is represented. If you go back to the previous slide, you can see the kernel dimensionality is represented like this. C0 is the number of output channel, then number of input channel, then number of kernel height, and then then number of kernel width. So this is how we basically deal with the multi-dimensional input data, multi-channel input data. So as you can see in this example, it is not necessarily that if the input channel is 2, output channel has to be 2 maximum. The output channel can be 4, 5, anything. It is not dependent on the number of input channel. So if you apply another kernel, another 2 kernels, suppose you are applying. So instead of 2 3D kernels, if you want to apply 1, 2, 3, 4, if you want to apply 4 3-dimensional kernels, then the number of output channel will be 3 and 4. So in that case, you will have a kernel like this, where the first dimension, which is the number of output channel, that will be 4. In general, we always try to increase the number of channels. So if your input is 2 channel, we always prefer to output to have a more number of channel than 2. So if input is 2 channel, we may want output to have a 4 channel or 5 channel. We try to reduce the resolution of the image, but we always try to increase the number of channel of the output image. Okay, that is related to how you can deal with RGB image data. Now, there was a very interesting question from the participant that what is the logic of pooling? So pooling, let me explain with an example. Pooling can be two types in a convolution neural. After applying the convolution neural network, we must use a pooling layer. Now pooling can be two types. max pooling and average pooling. So suppose this is your hidden representation after applying convolution. So there was some input image, you have applied some kernel, and by that got a hidden representation like this. Now if we apply max, you can apply max pooling or you can apply average pooling, and we can get this kind of outputs. So max pooling, here the pooling window is 2 by 2. And max pooling, we consider the maximum value in the pool. Average pooling, we take the average value in the pool. So it will be 1 plus 2 plus 3 plus 1 plus 2 plus 4 plus 5. So in this case, it will be 3 because 1 plus 2 plus 4 plus 5 plus divided by 4, sorry, 4. So it will be 3 plus 9, 12 by 4 is 3. So it will have a value 3. So average pooling works like this below and max pooling works like this in the above. That is how pooling works. Now people may ask, what is the benefit of having pooling? Benefit of the pooling has been explained in my next slide. So suppose this is your original input image. Now, suppose image is altered. In this portion, certain pixels position has been altered. Now, if I am going to consider, suppose I am going to consider the max value in this region. Suppose I want to consider the max value in this region. So in that case, even if some pixels has changed its position value, still we are going to get the same output. So if some pixels are altered, then also that will not take into consideration in the next convolution layer. And that is one of the primary importance of pooling. Pooling make the data location invariant. So the another advantage is that pooling is going to take the maximum value. Like here, if I suppose this is my window, this is my kernel window, and in that case the beak is present. So you could have considered there beak is not present, beak is not present, beak is not present, here beak is present. So obviously this portion it is having a very high value, and in other positions of the pixels having a low value. But end of the day this window contain the pixel, so obviously it should have a high value. However, here no pixel contain the big, so it will have a low value. It will have a very high value. Now you can consider the average of those pixels, like here value is 0, 0, 0, 0.5, 0.6, 1. You can take the average values, or you can consider overall a particular pixel is there where peak is perfectly present and value is 1. So that is why I always say go with the max pooling instead of average pooling. Because if the feature is present in your data, it should have a high output value rather than some portion it may not contain that feature. So that should not degrade the value. So in average pooling, so as we can go back in the previous pixel before this, so suppose a beak is present. So here the beak of the bird is there. So that is why it is giving a very high value 9. Here they are also giving a quite high value because it is the near region to the beak. But here the beak was not there, so value was quite low. For hypothetically choose this, so obviously this should be 7, this should be 5, like that. So these are all having high value because in the vicinity weak is there. Here in the vicinity weak was not there, so value was low. So you can either consider the maximum value out of it, like 9, or you can take the average of this, which may be a lower value like 7. So I always suggest go with the maximum value. So if your window contain the desired feature, you should say firmly that the feature is present. If your window contain the feature, you should not you can ignore the other pixels which basically do not contain the feature. That is the concept behind max pooling. So it is going to give you the maximum. Even some pixels in the window do not contain the feature, still it is going to give you a high impact that overall in this region the feature is present. It doesn't matter in which pixel it is there. Overall the feature is available in this window. That is important. So I have found out this image or this window contain the feature. I am not telling in which specific position the feature is present, but I am telling you firmly that the feature is present in that particular region. That is the concept of pooling. Okay. So end of the day, suppose this was your input layer, then pooling, this was your input layer, then convolution layer, pooling layer, and there may be a repetition of convolution layer, pooling layer, and after that, so after pooling layer, as you can see, after the pooling layer, input is what? Input is a grid form, no? Input is not one dimensional. Input is again maybe m cross m. So after pooling layer also, the input is in grid form, like this, grid form. But end of the day, output layer is what? Output layer is always one dimensional. Like suppose there are class 5, 4 classes are there. Class 1, class 2, class 3, class 4. So it is going to end of the day give you some output like 0, 1, 0, 0. So the data belongs to class 2. Suppose the value is 0, 1, 0, 0. That means the data belongs to class 2, not class 1, class 3, or class 4. So output is always one dimensional. So that is why end of the day, after the last pooling layer, you need to flatten the two-dimensional or multi-dimensional data into one dimensional. So if your data is like this, you should flatten it like 1, 1, 0, 3. You should flat in a single dimension because output layer is always single dimension. And then only you can multiply like this. Always two consecutive layer having some same amount of dimensionality, else it cannot be computed correctly. So this is why a flattening layer is required. Before, after the last pooling layer, you need to flatten the input. So suppose the number of node becomes now 100. So it is the number of 100 node after, and this is the output layer. Maybe here in this example, the number of node in the output layer is 4 because 4 classes is there. So here the penultimate, the last hidden layer having the number of node is 100 and the output layer having the node of 4. Now again, if you from directly a number of 100 nodes, if you want to converge into 4 number of nodes, the network may show some overfitting characteristic because the number of weight need to be, number of hidden node need to be decreased gradually and not drastically. That is why sometime in between the flattening layer and output layer, we add some in between hidden layers that we call the dense layers. So as number of node is 100 and number of output is 4, so deviation is too much. So we can use a in between dense layer where the number of hidden node will be 50. So this layer having 100 number of nodes, dense layer having 50 number of nodes, and output layer having 4 number of nodes. And it can simply work like a multi-layer perceptron or any feed-forward neural network, and like all the flattening node will be connected with all dense network weights, and all dense layer weight will be connected with the output layer nodes. So there is a full connectivity, and due to that reason this is called dense layer, because it is dense layer. Why? Because all the flattening layer nodes are connected with the dense layer nodes, and all dense layer weights are connected with the output layer nodes. That is why this layer is called dense layer. And sometime people ignore this flattening layer and dense layer, and they use a concept like global average pooling. And that is another concept where people ignore this flattening and dense layer. So in that case, this is your last feature layer. Here we can see it is grid form only. So this is fully connected layer, and here we do not do any fully connected kind of things, rather than we based on this feature map only will classify. So global average pooling ignore the flattening layer, dense layer, and it can directly try to classify the data from the last feature map layer. So that was the overall theory behind the convolution neural network. So this is image. You can apply convolution max pooling multiple times as you wish. After that, you can use flattening layer and dense layer or fully connected feed-forward neural network. And after that, you can use output layer to classify. But you can skip this whole part and you can simply use the global average pooling layer to get the output. It will have a less computational cost. So it will have a less computational cost. That is the concept of overall convolution neural network. So till now, if anyone having any question, then they can ask me. After that, I will quickly jump into the hands-on training, and I will show you the code that how like this is LeCun. LeCun has invented the first convolution neural network, where this is the input image. As you can see, this is the height and width of the image. After that, he has used one convolution layer, one pooling layer, next convolution layer, pooling layer, after that fully connected layer, dense layer, and output layer, like I have discussed, and implemented a image classification task where this is the MNIST dataset, MNIST dataset. The dataset contain handwritten digit from from zero digit to nine digit, and 10 number of classes are there, and it tried to classify all the handwritten digits. So I am going to demonstrate in my Google Colab how it can be implemented this linet. But before that, I would like to receive questions from our participants.
May I ask, sir?
Yes, sir.
Hello.
Please. Yeah, please ask.
Very good afternoon, sir. Very
Very
thank
good.
you for very nice presentation. Sir, my query is this one. When we talk about the global average, as you said that in the global average, we are having less computational cost. Is it
Yes.
any drawback associated with global average as well? Because as far as the theoretical point of view is concerned, global average is find to be very better one as far as the leniency latency term is concerned, because ultimately processing cost and time is also comes into the picture. So if we go for the global average, in my opinion, there will be lesser latency. But at the same time, is there any drawback associated with that one or not? I just want to ask that one.
Yeah, the thing it was a very nice question. So what I would like to tell you that in case of global average pooling, obviously there is a lot of advantage from computational perspective, but the global average pooling, as currently everyone is prefer global average pooling only instead of flattening layer and dense layer, because that will be computationally intensive. Though so overall, I would go for global average pooling layer only instead of fully connected layer. But there is a catch like this, as we are always go for the computational speed up. Sometimes it may ignore. Like suppose your pooling layer and convolution layer. Suppose it has missed. Like as you can see in my last slide, it was visible. So it has already decided the number of channels. Now global average pooling layer in a last layer, you said there are suppose eight channels are there. The output channel is 8, and based on that it is going to classify into 8 channels. So if your convolution layer and pooling layer has done any mistake, that cannot be further rectified by the dense layer. So there is an additional MLP layer is there after the pooling layer, last pooling layer, and that can fine tune your result. So suppose if there is still any mistake in your pooling and convolution operation, then that can further fine tune by your fully connected layer along with dense layers. That final fine tuning opportunity is not there in global average pooling layer. So you can say that if there is any modification is required by further running the feed-forward neural network, that fine-tuning is not performed in global average pooling layer. So if there is any mistake, it will proceed. So that is a issue. That is the issue with your say that is the issue with your fully connected layer. Sorry, global average pooling. Rest is okay.
Okay, sir. Thank you very much, sir.
Okay, okay. Okay, any other question from participants?
Good afternoon, sir.
Yeah, please.
Yeah, sir, I have a doubt. Like, can we apply this CNN with tabular data?
Okay, that is an interesting question. But you want to apply tabular data, you want to apply tabular data in 2D form or in a 1D form?
Sir, because let's say the table is containing many columns. So, what I need to do if I
Okay, no,
want to
no,
apply?
no, no, no. No, no, I just need to ask you a question. You want a tabular data, will it be in a 2 by 2 grid?
No, sir, not 2 by 2 grid. I have several columns and several rows.
Oh,
So,
that means it is a 2 by 2 grid now. So one dimension is number of rows and another dimension is number of columns. So it is a 2 by 2 now.
yeah, yeah.
So how you feed the, so there is no problem. You can do that. Because end of the day, CNN is also receiving the data in a tabular form only, na 2 by 2 as I have shown you. So you can feed the tabular data in a convolution neural network, but I suggest you to have it in a square matrix form. So uh,
Okay.
like uh, like suppose the number of rows and number of columns, if they are varying, till now in my images I have shown you, like you can see in my image, suppose image is 640 cross 480. So if your number of column for all the rows, if they are same, then there is no problem even if they are not squared. But suppose your some feature having 10 columns, some row having 10 column, and some row if they are having 5 columns, then it you have to apply padding. End of the day all the rows should have equal number of columns, then that particular tabular data you can feed into convolution neural network, there is no problem.
Okay, sir, but my table that I'm considering, it is having different types of data. So what should I do in that case?
Okay, I'm not getting your problem. Can you be a little precise
Like
by
let's say in a row, the first column is having some numeric values, continuous values. In the second column, I am having some categorical values. In the third column, let's say I am again having some 0 1 values, binary values. So I have different types of data present in my table. So
okay, okay.
can I do something with CNN in that case?
Yeah. How I can suggest you is that, see, end of the day, if you have to convert those categorical data by some numerical values, like you can apply one hot encoding or something like. Suppose you are having a feature like whether male or female. So you cannot directly apply male female features now. So you can use one hot encoding. So for gender, you can use two columns. So if that person is male, maybe you can use 10, and if it is female, you can use 01. So those categorical features need to be converted by numerical features using one hot encoding. So after that, obviously, you will have some n number of columns, and all the, I hope all the rows are representing the same type of samples, now.
Yeah.
Yeah. So in that case, you will obviously the number of columns only increase. So you will have maybe n number of rows and n number of columns. So it will be a m cross n matrix, and that matrix you can feed into the convolution neural network. But yeah, there is one interesting question. The data on which you want to work. You want to perform classification operation or forecasting operation or any simple approximation task. What kind of task you want to do?
I want to do classification.
Okay. You want to do classification. Now, this tabular data, when you are feeding the tabular data in a convolution neural network, the question lies that do you want to take the leverage of those two principle of the convolution neural network? Like, do you want to take the leverage of the neighborhood property? Suppose your data do not need to have any neighborhood property. Like when you are feeding your tabular data in a CNN model, so obviously the next consecutive rows and next consecutive columns are in the neighborhood. So obviously they are trying to influence each other. I hope you are getting my point.
Yeah, I'm getting, but here these are all discrete.
Yeah, so if there is no relation between it, then basically you are not going to take the advantage of the CNN model, or those CNN property are not useful in your problem domain. Then there is
Okay.
no logic of using CNN. You can use CNN, but CNN majorly try to focus on neighborhood region, and sometimes it ignore the distant feature, give more importance to the near about feature. So column M and M plus 1, as they are adjacent columns, they are trying to influence each other, which may not be right in your example. No? So I suggest
Okay.
you, it's better to go with the other kind of neural network, like you can go with RNN kind of, or simple deep neural network you can use. The neural network with multiple hidden layers.
Okay, sir. Thank you, sir. Sir,
Okay.
thank
Any
you.
other question? Any other question?
Sir.
Okay, if there is
Sir,
no
can
question,
you, sir, yes, sir,
yes,
actually,
please.
sir, where is that is the dropout layer, sir?
Okay, that was a nice question. Actually, dropout layer is a customization of CNN. In my first discussion, I was typically talking about the convolution neural network. I was typically talking about fundamental of convolution neural network. Now, dropout is a concept in a neural network that can be used. That is a add-on feature that can be used to any neural network. But obviously, it is not the core component of the convolution neural network. So obviously you can use dropout in any neural network model, and CNN is nothing new. So you can use dropout layer in CNN as well, but it is not the core component of a convolution neural network. Dropout is precisely used when there is a overfitting in the data. So you are dealing with the complex image data, and maybe some layer is
Sir, can
influencing the
you
other
give the one
layer.
example, sir? Sir, can you give one example, please?
Okay,
Because
suppose
I
you are
don't
dealing
know.
with okay, have you worked on any image data?
No, image data I have, sir, but where is the dropout? How
Can
to
can you
select
can
the
you tell?
dropout?
Okay, can you tell me any image data on which you have worked on? Any image data which you have used? Name of any image data set? Okay, am I audible, sir?
Sir?
Yeah. So okay, just tell me the image data set on which you have worked. I will guide you further.
No, sir, I don't have, sir.
Okay, okay, no problem, no issue, no issue. Let me take. Suppose you are working with a very simple image dataset. For example, MNIST dataset. Have you heard the name of the MNIST dataset? The hand digit recognition dataset.
No, no, I don't know.
So there is an image dataset, MNIST dataset, which I am going to show in my demonstration. So let us not wait further, because it is already 4 past. So let me share my screen. Huh? Give me a moment. Let me share my screen. Okay, 1 second. Huh?
Yes, yes.
So is my screen visible?
Mm, yes, sir.
Okay, so
Yes.
in that case, you can see that this is my data. Suppose these are my image data. Is 504192131, are they visible to you?
Yes, sir. Yes.
Ah. So in this example, you can see that these are the images, and this is a very simple data set. So in this kind of simple data set, there is no chance of overfitting and all. So obviously, you do not need to use the dropout layer, or that batch normalization layer. But there are a lot of complex data sets there. You may have heard the data set of ImageNet data set, or the Cipher 10 dataset, Cipher 100 dataset. These are a very well-known standard datasets. These datasets are not simple datasets. So in this kind of datasets, you can use dropout layer. The core concept behind the use of dropout layer is that it helps you to get out of overfitting. Overfitting is a scenario that your model is working perfectly in case of training data, but your model is not working well on the test data. So why it happens? When your data having dependency on your weight vector. So weight vector dependency we want to reduce, and to reduce the weight vector dependency we use a dropout layer. So dropout is a concept that is used to minimize the impact of overfitting, which can happen in any neural network model. So if you feel your dataset is complex, if your dataset is giving very good performance during training but it is failing during testing, definitely your model having overfitting, and to resolve it you must use dropout layer. But if your data set is not having any overfitting issue, I suggest you do not need to go for dropout layer. It is not necessarily that you have to use dropout layer because everyone is using. It depends on your application. If it required in your application, go for it. If it do not require in your application, you can skip it. Okay. Okay. In the meantime, okay. Are you satisfied with my answer?
Yes, sir. Yes, sir. Yes, sir.
Okay.
Because
Okay.
that fundamental, I don't know. Okay, I understood, sir. Now.
No problem. You have started joining this course, and this is only the second day, so we have lot of new things to learn on. So no problem. We have lot of time, and I hope you will have come up with a very good knowledge when we conclude our event. No problem. So so in the meantime, I would request Asik. He is going to demonstrate. Asik, are you available in the meeting? Hello, Asik. Okay, so I would like to request Asik to give a demonstrate on his coding, that how image data can be used by CNN model for classification task. And after that, if I get any time, I will also demonstrate how standard convolutional neural network can be used and used for real life data. So give me a minute. Let me try to contact with Asik.
Good afternoon, everyone. Am I audible? Hello. Am I audible?
Yes, you are audible. Perfectly audible.
Yes, you are.
Till now, we have seen the implementation part. We have seen the theory part of CNN. Now we will do a hands-on coding in CNN on the image dataset. Is my screen visible? Is my screen visible?
Yes.
Hello?
Yes.
Yeah.
Yes. Yes.
So I will do it. I will implement the CNN in Kaggle, and the dataset is a flower dataset. It contains several images of 5 types of flowers, mainly daisy, dandelion, rose, sunflower, and tulip. So, it is a classification task. We will develop a model, and then we will try to classify each image that in which class the image belongs to. So for that reason, we need some dependencies and some modules in Python. So at first we need to import that modules. So let's start with the modules. Let's start with the importing of the modules. At first we need OS. We need to import OS, and then we need pandas, and we need to plot some graphs. So we need matplotlib. So we need to import that also. And we also need C1. Okay, now let's start with the dataset. Let's start with the reading of the dataset. So to start with the dataset, we need to fetch the directory in where the images are So at first, the directories of the images is directory of DC. We can copy the directory from here, and we just can paste it here. And similarly, we can access all the images by using these directories. Let's change the Okay, these are the directories of where the images are currently in, and now we will try to read the images by using CV2. And so to read the images, we will just define a function that will help us to read the data. Here we will just add two variable. One is flower type and another one is directory. And for each image in so to access all the directories, we need to import another dependency, that is tqdm. Now we need to assign label to each of the data. I mean, if to for the images of rows, we will assign the label as rows, and for sunflower, we will assign the label as sunflower, and so on. So to label the data, we will again write a function, so that will help us to assign the label to the data. Let's write the function here. Once the labeling is done, now we will try to merge the image and the label, and we will append the merged data in the array. So we will just take two arrays. One is x and another one is z. Just naming the arrays accordingly, and the path will be, we'll start path dot join dir. So this will be the path to the data, and then to read the data, to read the image, we will use cv2. And we will just resize the image according to our need. So we just want to resize the data according to our need. Then our need, we want to resize, let's say it is 150 pixel. So we will resize the image to 150 cross 150. And then we will append the image to the x array, and the label to the y array. Now let's run the code one by one. Okay, so here is a mistake. So writing the function is done. Now let's start with the image of Daisy and so this function will label all the flowers in the folder Daisy to the label Daisy. Okay. So here is a error coming from this. So let's try to resolve this error. Okay. Okay. CB2 no is not imported. Okay. Now label all the flowers one by one. The next flower is dandelion. Okay. And the next is rose. And the next is sunflower. Now labeling of all the flowers are done. Now try to visualize the data. I will just randomly pick one flower from one class and try to plot that image. So to plot that image, we'll need the help of matplotlib. So okay, so so we will plot 5 rows and 2 columns, uh, two uh, two images from each class of the flowers. gene. So for each row and for each column, we'll just be running two loops. Great. Okay. So we need to import the matplotlib as plt. We also need styles for matplotlib. And now in this section, I'm facing some error. Maybe it's because of the version issue. So now let's start. Let's move to the next section. Let's import the label encoder. Let's go to the model prediction and encoding the model, encoding the data set to feed into the model. So to fit into the model, we first need to encode the labels using label encoding. So in this case, we will use one hot encoding. In one hot encoding, we just transform the categorical data into numeric data. Here the labels are we just mark the label as the name of flowers. So we will use one hot encoding to transform the labels into the numeric data to fit into the model. So in here we will use one hot encoding. So to use one hot encoding, we need to import that. And so to import that from Keras, we need to import one hot encoding, that is label encoder from scalar dot reprocessing dot reprocessing import label encoder. Okay. So now we will use this label encoder to encode the labels of our dataset. Label encoder y equals to only dot heat transform z. If you remember, the z is the array where we just appended all our labels, and we will so we again we need to import the two categorical from the scalar module. Keras dot import by this np.array function, we will transform we will transform our dataset into a numpy array. So numpy array can be fed into the CNN model easily. So for that reason, we will just transform it into a numpy array. So encoding the dataset is done. Now we have to split the dataset into training set and testing set. So for that reason, we will use 70% of the data for training and the 25% for testing. So To split the data, we need to include another module, that is train test split. History learn dot model selection import train test split. And okay, so by using train test split, we will split the data set into training set and testing set. So the training set, suppose we will name that as X train, X test, Y train, and Y test as to train test split, Y test size equals to 0.25. 0.25 means here 75% will be given to that training set and 25% will given to the testing set. And suppose random state is 42. It is just a random seed that whenever we split the data set using this random state equals to 42, we will get the same split again and again whenever we split the data set. Now run this section. Invalid syntax. Okay, here I put 2 equals to, it will be only 1. Okay, finally this section is done. So now splitting the data set is also done. Now we have to build the model. So to build the model again, we need to import some of the modules. So let's start importing the modules. So we will import from Keras modules, import sequence. And we need some of the layers like dense layers. So we need to import dense layer also, and we also need optimizer. We will use Adam optimizer here, so we will just import Adam. And also flatten layer will be needed, and also activation layer. Activation layers. Run this section. Here into bonus. Okay. Also, I think we will need some more layers like convolution layers and max pooling layers. Okay, these are the modules we will need, so we just imported that modules. And now let's start with building the CNN model. So the equals sequential. So this is just the initialization of the model, and then we will just add more layers one by one to the models, to the model. Here at first we will just add one convolutional layer with filter equals to 32. Kernel size equals to 5, 5. It is a 5 cross 5 kernel, and padding will be same. And we will use activation function. Value inputs is 150 plus 150, comma 3. Here 3 is for RGB, red, green. Here it is 3 is just to define that the image is in RGB format. Okay. Now now we will add one max pooling layer. Max pooling layer. Okay. Now we will add another convolution layer. In this time we will use filter size equals to 64, and kernel size will be 3 cross 3. We are decreasing the kernel size here. Padding will be same. And activation function, we will use a ReLU again. And again we need to add another max pooling layer. Here also we will use the pool size as 2,2, and we will use stride here also. We'll just add another layer of convolutional and max pooling layer. In this time we will use 96 as the filter size, and we'll again add another same type of layers. So just copy and paste, and then we will flatten the data in 1D vector. So at the end we need to flatten the data. So we will just use flatten module here, and then we will add dense layer to get the output. Dot add the dense layer will be 512. And then we will add the activation layer. Activation layer. And we will use the activation function value as activation function. And then after the final output layer will be another dense layer. In this case, we all know that in output layer, if we try to classify multi-class classification, we need to use softmax. So at the output layer, we will use softmax as activation function. Okay. So preparation of our model is done. Here's some error. Let's solve the error. Y92. Okay. Here it will be equals to yes. Krishna Kumar. Hello. Yes, you can talk.
Dear participant, if there is any question, please ask. Dear participant, do you have any question? Please ask. Okay, dear Asik, can you share this code with our participants so that they can practice?
Yes, I can share the code. Sir. I can
Okay,
share the
so
link of this code in the chat box.
okay, you can share it in chat box as well as you can share the code in WhatsApp also in future. WhatsApp group.
Okay, sir. Should I share it now?
No, if there is any confusion, then you can clean it and after that you can share by the evening. No problem with that.
Yes, sir.
Okay, dear students, is there any question? Please ask, dear participant. Is there any question?
No, sir. Right now there is no question. Everything is very fine.
Okay, okay, thank you. In that case, I would like to, okay, tell me.
Hello, Asik. Yeah, I have a
Yes,
confusion. Can we know who can decide how many, convolutional, these filters, layers, and how many pooling layers one has to, add?
okay. This is basically a customized CNN. So here we can just add layers and remove layers, so we can get a maximum accuracy. So according to that, we can change the layers. And here I am just demonstrating a customized CNN that I am considering four convolutional layers and one and two dense layers. So you can add any number of layers here
I got-
also.
So we can keep on, adding these both of the layers unless we will get our results that are very much accurate. Yeah.
Yeah.
Okay. Great. Okay. Thank you.
Is there any further queries of any student, or shall we end the session?
Hello.
Yeah.
Yes.
Kindly share this code, please, and all the PPT, that sir was discussing earlier, please.
Hi, hello.
Yeah, that will be shared.
I'm audible, sir.
Yes. Yes. Everything will be shared to you with you.
Hello, sir.
Hello.
Yes. Yes. Yes.
Like we want to run the huge amount of data at a time using CNN. Okay, sir. And how we can make as a two object invariance?
Yes, sir, I think you need to little refine the question. Could you be little more specific?
Okay, so we have like 20,000 medical data. Huh?
Okay.
Okay. In that, somebody
Mm,
is injured, somebody is not injured. So using CNN technique, how can we separate both the images?
Okay, so if I understand it properly, the question is that you have 20,000 images, and some images represent someone is injured, and the other images is representing that person is not injured. So this is a binary classification problem.
Binary classification in CNN.
Yeah, no, I'm talking about this is the data set. So your data set contain two different type of images, injured and non-injured, and you want to apply CNN to classify whether someone is injured or not. Am I right?
Yes, sir.
Yeah. So in that case, you can use the standard CNN like the CNN, LeNet, AlexNet, GoogleNet, Inception models, VGG. There are a lot of standard CNN models are there, which has their fixed architecture defined by the scientist. You can use them, or like ASIC has implemented a customized CNN model that can also be used and check its performance. But while checking the performance of the model like yours, your dataset may also contain the data imbalance issues. Means, are you suppose only the 100 images are there for injured patients, or the rest of the image maybe of weak participant, sorry, maybe of the non-injured. So is your data set is balanced one or imbalanced one?
It's normal balanced mode only. All data will be
Okay,
same.
okay, no, I would like to know that the number of images of injured people and the number of images of non-injured people, are they more or less same? So what is the number of
We
images
don't know
among
that.
the?
We don't know
Okay,
that.
so you need to know that, sir. So basically, yeah, Asik, you can conclude. You can stop your presentation if there is no further question. So, but I would like to get back to you, sir. So first of all, you need to look into those data. So because your neural network performance also depend on the data set. Based on the dataset, you are supposed to use your neural network model. So you need to know your dataset first. So suppose if your dataset is a balanced one, in that case, it is lot easier task to do. In that case, you use any standard CNN and try to take its classification accuracy. But if it is an imbalanced one, suppose only less number of representing from a class and majority of the sample is from a different class, in that case, you need to take into consideration the precision, recall, AUC, those things also you need to take into consideration. And after that, based on the requirement of your model, like whether it is overfitting or not, whether it is having class imbalance problem or not, based on that, you have to change your customize your model recurring fulfilling the need of the requirement of the data. You're getting my point? So as a machine learning engineer, first of all, we need to know about the data. So first of all, you can use any standard CNN model. You get to know what are the issue with the data. What is there any overfitting not or there or not? Is it taking too long to train or not? Whether there is a quick convergence or a slow convergence. These are the things you have to analyze from the data, and based on that, you have to customize your model. So your model performance is specific to the dataset. It is not like that a model is going to work with respect to any dataset. So you have to tune it according to your data. That is the answer currently I can give it to you.
Okay, yes. I'll try with my data set because last time taking 2 hours, 3 hours, but result was not coming. It's loading only coming.
Okay, so in that case, you need to look into your machine configuration also, and you need to know how many free parameters or weights you are considering in your neural network model. The less number of weights you are considering in your model, less time it should take for converging or giving you the result. So you look into it and get back to us.
Okay, sir. Thank you so much.
Thank you. Is there any more query?
No, it's okay, sir.
Okay, okay. No, is there any more query from any other participant? Yes, I would like to request Deepsika to conclude the session.
Yes, sir. Is there any more queries or we shall conclude?
No, thank you so
Okay.
much for learning. It was a great session. Thank you again.
Okay. Well, first of all, we truly appreciate Ashik for his time and efforts sharing his research knowledge. And thank you so much, Prasenjit sir, for your insightful and engaging session. With this, we are concluding today's session and we look forward to see you all in our upcoming sessions tomorrow. So thank you. You all may leave.